Hello, in this video we are going to be looking at section 9.8 where we discuss higher order derivatives. We're going to start with a little bit of background. So recall that a derivative of a function is actually a function in and of itself. So you can imagine that if you have something that's a function, you could take the derivative of the function, so the derivative of a derivative, and we would call that the second derivative. So if f prime represents the first derivative, then f double prime is going to represent the second derivative. Now, there's a lot of different types of notation that could be shown that ask for the second derivative. So y double prime would ask about a second derivative. This notation here that looks like d2y over dx squared, the way you would read that in English is the second derivative of y with respect to x. And then in this last set of notation, the derivative notation kind of looks like an operator. It's the second derivative of the f function with respect to x. So I will typically in these notes just use f double prime or y double prime. Let's look at an example where we find the second derivative. So starting out with this, before we can even find the first derivative, we need to rewrite the y function in a format that is going to allow us to think about using some of the rules we have developed so far. So 3x squared is fine, but I have difficulty thinking about the cubed root of x squared and how the rules apply to it. So I'm going to rewrite this as x raised up to the 2/3. Again, if you're not very familiar with how this algebra rule of converting a root to a power, the index of the root, the 3 here, is going to be the denominator of the exponent of your of the variable, and then whatever exponent the variable previously had is going to be the numerator in this new fractional exponent, this new rational exponent. All right, so that is just rewriting the function, but now we need to keep track of which derivative have we computed. So first of all, let's compute y prime, which is the first derivative. Actually, let me write this over here. Y prime is equal to, I apply the properties we have discussed. This is going to be 6x to the 1, then minus 2/3 x to the, now the new exponent I'm about to write, what I think about is I think about the previous exponent minus 1. So 2/3 minus 1 would be 1/3, sorry, negative 1/3. And that's my first derivative. Now I get to think about the second derivative. So the derivative of 6x is just 6, and then when we think about the derivative of this next part, the exponent multiplies to the coefficient, so a negative times a negative is a positive. 2 times 1 is 2, 3 times 3 is 9. Then it'll be x raised up to some new exponent, and we always take the previous exponent, subtract 1. So when we do that, the new exponent we're going to get is negative 4/3. And if it's helpful, just write this off to the side. Negative 1/3 minus 1 would be the same thing as subtracting 3/3, because 1 and 3/3 are the same. So then this is what I'm thinking about to come up with that exponent down there. Now we have done it. We have computed the second derivative. So really it is just a derivative of a derivative. Now when you're showing your work, it's very important to use the proper notation. Y was this function, y prime was this function, y double prime is this function. And your work will lose a lot of meaning if you aren't showing y prime and y double prime. Okay, let's look at another example. So we could also find third and fourth derivatives. Let me just give you some notation. The third derivative typically just gets called f triple prime, or the third derivative of f. Anything beyond 3, we stop using these hash marks for. So I'm going to say fourth and beyond. You would just say f, and then you would put parentheses 4 like that. If it was a fourth derivative, it would be, you would just insert any other number. If you wanted a sixth derivative, you put a 6 in there. Okay, so given this function, let's find the third derivative of f. Well, first of all, I'm going to rewrite f so that I can take the derivative. We know that the square root of a expression would be the same thing as that expression raised up to the 1/2. So this is just a little bit of algebra to rewrite square roots into rational exponents. Next, let's compute the derivative of that. So f prime is equal to 1/2. We get to apply the chain rule in this example, so that's x minus 5 raised up to the, let's see, the new exponent would be 1 less than the previous one, so that'll be negative 1/2. Now, because this is a chain rule problem, the chain rule says you first of all do the derivative of this outside function, leave the inside alone, but then afterwards you have to tack on the derivative of the inside. So in this case, the derivative of x minus 5 is just 1. Now right now it may seem like that wasn't important because it was just a 1, but if you had had any constant in front of this x, like if it had been 2x minus 5, then we would have an interesting number, and then this would just start to compound in the problem. So important that we notice that it's there. I do want to simplify this before we continue on to the second and third derivatives. The only thing you can simplify is 1 times 1/2 is going to be 1/2. Then it's x minus 5 raised up to the negative 1/2. All right, let's do the second derivative. Second derivative would be, now I'm looking over here when I'm trying to decide what the second derivative is. The exponent multiplies to the coefficient. We can write that down as negative 1/4 times x minus 5 raised up to, we have a new exponent. It should be 1 less than the previous one was. So if we subtract 1 from the previous one, what we get is negative 3/2. We technically have to multiply by the derivative of the inside, which in this case, again, is just 1. So our answer here is negative 1/4 times x minus 5 raised up to the negative 3/2. That was our second derivative. Now we compute our third derivative. When you compute your third derivative, again, you're looking over at the simplified version of the second derivative. We want to take the derivative of this function. So think about how that exponent and the coefficient are going to interact. Negative times a negative will be a positive. 3 times 1 will be 3. 2 times 4 will be 8. Then we have the x minus 5. We have a new exponent. You have to take your previous exponent and subtract 1 from it. So when we do that, let's see, negative 3/2 minus 2/2 should be negative 5/2. Technically, you have to multiply by the derivative of the inside function afterwards. All right, so last little bit of simplification. 3/8 times x minus 5 raised up to the negative 5/2 is our final answer here. Okay, next question. This time we have a polynomial, and we're going to notice something at the end. I don't want to spoil it ahead of time, but once we get to the end, we should notice that something has happened. So we start with y, which is x to the 6 minus 15x cubed. Then we compute y prime. So derivative goes like this. 3 times 15 is 45. That's x squared. Then we compute the second derivative. 6 times 5 is 30. We reduce the exponent by 1. 2 times 45 is 90. Reduce the exponent by 1. Third derivative is 120 x cubed minus 90. And then the fourth derivative is equal to 3 times 120 is 360 x squared minus 0. So we would just leave it like this. Sorry, I apologize. I'm just now noticing that the instructions said find f, like the fourth derivative of f, and then we didn't talk about f. So all of my notation talks about y. So I'm just going to change this notation to say the fourth derivative of y. Find the fourth derivative of y. Okay, so now this process looks proper. We have answered the question. The pattern that you might have noticed is that with polynomials, the exponent always reduces by 1, but since it started out as like this nice positive integer, as it reduces, we're just getting closer and closer to 0, and in some cases, if the if we're taking a large enough derivative, then some of the terms are just going to disappear entirely. So we had x cubed, the first derivative turned it into x squared, the next derivative turned it into just x, then we had a constant, and by the time we hit the fourth derivative, it was gone. So if there had been any other pieces after this, like if I'd added on, like if I add on like plus x squared minus 13x plus 15, if there are these little pieces at the end, then because we took a fourth derivative, all of these will eventually become 0 along the way. I guess this one turns into 0 first, then this one, and eventually the x cubed terms also went to 0. One last example before we get into some application questions. So let's find the fourth derivative of f if you know that f is equal to 1 over x. First of all, let's write what f of x is. F of x is equal to 1 over x, but that's really x raised up to the negative 1. It's going to be important for you to think about it in this way so that we can apply our derivative rules. 1 over x, you would have to use a quotient rule, but really it's not an efficient way to think about it. So next we want to compute the first derivative of f. Okay, we apply the property, exponent gets multiplied out in front, the new exponent is 1 less than it used to be. Second derivative, multiply exponent times the coefficient, exponent is now 1 less than it used to be. Third derivative is negative 6, x to the negative 4. Fourth derivative is now going to be 24x to the negative 5. And that's it. That is our answer. All right, let's look at the acceleration problem. We need to begin with a little bit of context. The second derivative of a position function is going to represent the instantaneous acceleration of an object. So a positive acceleration implies that your velocity is increasing with respect to time. A negative acceleration implies that your velocity is decreasing with respect to time. And then if the velocity remains constant over an interval, then your acceleration would be 0 on that interval. So it's basically a rate of change of your velocity. So for example, here we have a formula that describes the distance an object travels as a function of time. So our function b describing distance means this is just a position function, and we want to compute acceleration. The idea here is that your first derivative will be equal to velocity, and your second derivative will be equal to acceleration. And the question at hand is, what is the acceleration of the object when time is equal to 4? Okay, so first of all, s prime would be equal to 160 minus 32t. That is your velocity. Velocity is equal to the first derivative of the position function. Acceleration is equal to the first derivative of your velocity function, which would be the same thing as saying the second derivative of your position function. So we get negative 32 in this instance. The question says, what is the acceleration of the object when time is equal to 4? So if t equals 4, the second derivative is equal to negative 32. Now this may seem weird to you to say it this way. The idea is that you would plug 4 in for, I guess, seconds. Time is in seconds. You would plug 4 seconds into the function to decide what the acceleration is. But in this case, what we have seen is we have a constant acceleration. So this might be because you took an object and you threw it up in the air, and then it's now falling down towards the Earth at a constant, with a constant acceleration due to gravity. But it's just whatever your acceleration is in this example, it's not based on time. We found that it was constant regardless of time. So there was nothing special about the 4 if you feel like you didn't use it. In some examples, if you had a different formula, you would plug the number in, but in this case, quote-unquote plugging 4 in doesn't actually yield you a different result. You just have negative 32 as your acceleration. It is probably worth thinking about what type of label is appropriate for acceleration. Just thinking about like having a position function, velocity followed by acceleration, we can talk about what those labels would be. Your position is a measurement in feet. Your velocity is feet per second. And then your acceleration is feet per second per second. So another way of saying that is feet per second squared. So down here, I'll say feet per second squared. Okay, lastly, let's look at a revenue example. In this example, let's suppose that the revenue in dollars from the sale of a product is given by the following function. Here, X is going to be the number of units sold, and we want to know how fast is the marginal revenue changing when X equals 100. So you want to be very careful with how you think about this. First of all, when we reference marginal revenue, recall that this is the first derivative of the revenue function. And if we ask, how fast is your first derivative changing? Well, to measure a change in your first derivative, an instantaneous rate of change of your first derivative, that's a question about the second derivative. So your revenue is changing. So you are thinking about, maybe I'll just write second derivative, S-E-C-O-N-D, second derivative. Okay, so we have R listed for us. Let's first of all compute R prime. This will give us the marginal. That would be 70 plus 1x minus 0.003x squared. Then we can compute the second derivative, so that would be 1 minus 0.006x. Okay, and so this is a measurement of the rate of change of your marginal revenue. Okay, how fast is the marginal revenue changing when X is equal to 100? What we would like to do is we would now like to just evaluate our double prime at 100. So that's 1 minus 0.006 times 100, which would be 1 minus 0.6, which should be equal to 0.4. So this is the rate of change of the marginal revenue. 0.4. If you want to give this a label, let's see. Your revenue function was in dollars. That means your derivative would be dollars per unit. That means your second derivative would be dollars per unit, which is a weird way to say it. So we'll call it dollars per unit squared. So this is $0.4 per square unit. All right, that finishes this section of notes. We really have just introduced the idea of how we compute a second derivative. We haven't really talked much about the implications of the second derivative, but in later sections we will discuss what is the meaning behind the second derivative. We'll discuss that a lot more. Definitely, like, if you know your second derivative is positive or if you know it's negative, that tells you information about the original function, but that's all stuff that's going to be coming up in the future.